In telecommunications, transmission involves communicating information in the form of a signal. It also pertains to the equipment and the systems that transmit, transport, and receive the information.
In program segments within other Telessentials courses, you've gotten a glimpse of how telephony evolved into the global communication system it is today. Within that system, there are many types of equipment that transmit, carry, and receive information. In this video segment, you'll see various means for connecting one person to another person located practically anywhere in the world. Transmission media tie together all of the devices and equipment that enable people and machines to communicate. Whether the transmitter and receiver are people or machines, transmission equipment and media are designed to permit information in the form of signals to be communicated clearly and accurately. The received signal always differs, to some degree, from the transmitted signal. When the differences are not acceptable, signal impairments must be reduced. Test equipment, often in the form of portable test sets, are used. There are many different types of test sets made, but they usually consist of some type of meter, such as an oscilloscope. The test sets are used to determine how much signal loss, gain, or noise there is in the transmission path. The test sets help isolate impairments in both analog and digital transmission systems. A major goal in equipment design is to keep signal impairments at a minimum. Most impairment testing occurs when equipment and facilities using the equipment are being designed. Ideally, refinements and improvements are made to transmission equipment and media before they're installed. In this program, we will look at three types of transmission facilities. The three types are wire, microwave, and optical fiber. Wire transmission facilities include open wire lines, twisted pair cables, and coaxial cables. Open wires were the first type of transmission medium. Signals on open wire lines were susceptible to crosstalk and noise from electrical power lines. Open wire is still used in some places, but has been almost entirely replaced by twisted pair cables. Twisted pair cables consist of insulated wires twisted together to make pairs. The wires are twisted to help reduce noise, such as crosstalk. Hundreds of wire pairs are put into a cable. The cable is usually insulated with plastic or wood pulp. Cables insulated with wood pulp hold from 600 to 3,600 pairs of twisted wires. Plastic insulation is used most often today. Cables insulated with plastic can hold from 600 to 1,800 twisted pairs. Twisted pair cables have an outer coating made of aluminum, steel, or most recently, polyethylene. Inside the cable, the wire pairs are separated and wrapped into bundles called binder groups. The pairs and binder groups are color-coded so they can be identified. Twisted pair cables are used in the local loop and in trunks. Since they're used in a similar fashion, let's examine the local loop. In the local loop, twisted pair cables span from the main distributing frame in the central office to the residences. Between the central office and residences, twisted pair cables are strung on the sides of poles. On this utility pole, the power company uses the top part of the pole. The telephone cables are located below the power cables. Twisted pair cable may also be installed in underground passageways or buried in the ground. Although twisting wires reduces interference from noise, it increases signal loss. For this reason, twisted pair facilities use various load coils. Load coils help to maximize the power of the signal through impedance matching. Another device in the local loop is a bridge tap. A bridge tap connects one wire pair in a cable to the smaller cable that runs into a customer's premise. Now, let's look at the twisted pair trunk equipment used for analog carrier transmission. Analog and digital carrier facilities have similar equipment. The facilities consist of distributing frames, channel banks, modulators, multiplexers, and repeaters. The first appearance of the trunk in the central office is on the distributing frame. From here, the analog trunk goes to the channel bank, where it's amplified, modulated, and finally sent to a multiplexer which multiplexes the trunk with many other trunks. Analog facilities use amplifying repeaters. Digital facilities use regenerative repeaters. They reconstruct incoming digital signals. Coaxial cable is used for analog and digital transmission. Let's take a look at coaxial cable now. This type of coaxial cable was designed for the L5 carrier system. It has many coaxial cables inside of it called tubes. A coaxial cable consists of an inner conductor and an outer conductor. The conductors are metal, usually copper. The conductors are separated by insulation made of plastic discs or beads. The advantage of coaxial cable over twisted pair cable is that the inner conductor in a coaxial cable is shielded by the outer conductor. Electromagnetic interference is prevented from causing noise in the transmission line. The electromagnetic interference may be in the form of radio frequency noise or low frequency noise from motors and industrial equipment. The outer conductor absorbs the noise. In twisted pair line, radio frequencies affect both conductors and cause noise in transmission. This L5 coaxial cable may have up to 22 tubes inside. 10 tubes are used to transmit, 10 are used to receive, and 2 are used as spares. Coaxial cable is most often used in carrier systems. Repeaters are spaced from 1 to 8 miles apart, depending on the cable size, type, and system.
Wires were the first type of transmission media to be used in telecommunications. Then later, techniques using microwaves were developed.
Let's first focus our attention on terrestrial microwave radio. Terrestrial microwave transmission uses transmitters, repeaters, and receivers on the ground. Microwave transmitting equipment includes multiplexers and modulators, waveguides to transport high-frequency signals up a microwave tower, and the transmitting antenna. Electrical signals from multiplexers and modulators are converted to electromagnetic radiation. Then they travel through waveguides from the radio transmitter to the top of a microwave tower. Waveguides are circular or rectangular shaped pipes. At the top of the terrestrial microwave tower is an antenna. Antennas used for terrestrial microwave transmission are usually horn or conical reflective antennas. Both types consist of a reflective surface and a feed horn. They both work the same way and are made of lightweight aluminum, plastic, or fiberglass. The electromagnetic radiation goes from the waveguide through the feed horn and is then directed toward the reflective surface. The electromagnetic radiation is reflected and concentrated into a directional beam. Microwave repeater towers are placed along the terrestrial route. These work like the repeaters we examined earlier. At the receiving end of the transmission, the microwave signal is reflected off the horn antenna's surface and is focused into a waveguide. It travels through the waveguide to the base of the tower and into the radio building. Satellite microwave systems have transmitters and receivers located in ground stations, but the repeater is the satellite orbiting in space. In an orbiting satellite, the equipment used to receive, amplify, and retransmit signals is called a transponder. With most satellite transmission systems today, 2 carrier frequencies are used, for example, 4 gigahertz and 6 gigahertz. A channel having a 500 megahertz bandwidth is divided into 40 megahertz segments and then is transmitted from the ground station to the satellite at a carrier frequency of 4 gigahertz. The transponder, while keeping the 40 megahertz segments separated, shifts the carrier frequency up to 6 gigahertz and then transmits the signal to the receiving ground station. A common type of antenna for satellite transmission is the parabolic dish. This kind of antenna is also made of lightweight aluminum, plastic, or fiberglass.
Because of the large bandwidth microwaves can transmit, they'll continue to be a viable medium for telecommunications.
Now let's turn our attention to another type of transmission facility, fiber optic systems. Like microwaves, light waves are a type of electromagnetic radiation. Light waves used for telecommunications are in the infrared frequency range, so we can't really see them. In this example, we're using visible red light to give you an idea of what the fiber optic light waves look like. Light wave transmission facilities consist of transmitters, receivers, and repeaters, as well as the optical fiber medium. Fiber optics transmit light, not electricity. Electrical signals are converted to light wave signals by diodes. The light wave signal is digital. Diodes transmit the light into the optical fiber. Two kinds of diodes that transmit light waves are injection laser diodes and light-emitting diodes. Injection laser diodes emit light in a narrowly focused beam. Light-emitting diodes emit light in a beam that is more spread out. Each fiber has an inner core and an outer layer called cladding. The inner core is made of very pure glass. The light waves travel through the inner core. The outer core, or cladding, is made of less pure glass. It physically protects the inner core and also helps prevent signal loss from the inner core. There are two types of fiber optic cable, single and multi-mode. Single-mode cable is used on high-capacity, long-haul transmission paths. This type of cable requires repeaters every 50 miles. Multi-mode cable is used on short distances and low-capacity routes. This type of cable requires repeaters every 5 to 6 miles. It is often used on small computer networks. AT&T uses this type of cable as a communication link between the various switching equipment frames. Individual fibers are put into cables. Two kinds of optical fiber cables are ribbon cable and stranded cable. Ribbon cable may have up to 12 flat ribbons inside. Each of the 12 ribbons has 12 optical fibers. Stranded cable has one or more inner units. Each unit has from 4 to 12 separate fibers. There are also wires inside to strengthen the cable. Both types of cables, ribbon and stranded, have several layers of protective coating. In fiber transmission facilities, repeaters are regenerative. This is because light wave signals are always digital. At a light wave repeater station, the light waves are converted back to electrical signals, digitally regenerated, converted to light waves again, and then retransmitted through fiber cable. At the receiving end of transmission, light waves are converted to electrical signals using photodetectors or photodiodes.
In this program, we've covered the different ways the telephone signal is transmitted through the network. We've seen open wire, twisted pair, coax, and fiber optic cable. You've also seen the facilities that each type of cable uses: modulators, multiplexers, and repeaters. We've even covered terrestrial and satellite microwave transmission. Over the years, as the transmission media and equipment have improved, the quality and quantity of information has increased. Transmission facilities are a crucial factor in the information age.
Please return to the CBT lesson.